Had a long day? This video offers more than 2 hours of calm explanations on how Mars and Venus could become habitable. We get straight to the point. Warming Mars, thickening the atmosphere and adding protection from the solar wind, cooling Venus, cutting carbon dioxide and lowering the pressure. You can fall asleep whenever you want. The audio stays steady and even. You rest and still wake up with a clear sense of what is technically realistic. Have you ever looked up at the red planet and wondered what it would take to make it habitable? Mars, our neighbouring planet, presents one of humanity's most ambitious potential projects, terraforming. While currently cold and inhospitable, with an average temperature of -60 degrees Celsius, scientists have theorized numerous methods to warm the Martian surface as the first critical step toward making it more Earth-like. The primary challenge with Mars is its thin atmosphere, which doesn't retain heat effectively. One of the most discussed approaches involves releasing greenhouse gases to create an atmospheric blanket that would trap heat, similar to what occurs naturally on Earth, but more deliberate and accelerated. Scientists have proposed manufacturing and releasing potent greenhouse gases such as chlorofluorocarbons, CFCs, or methane, which are many times more effective at trapping heat than carbon dioxide. These could be produced using local Martian resources through automated factories established on the surface. The advantage of this approach is that once initiated, it could create a positive feedback loop. As the planet warms, more carbon dioxide frozen in the polar caps would be released, further enhancing the greenhouse effect. Another fascinating method involves the strategic placement of giant orbital mirrors. These enormous reflectors would be positioned in Martian orbit to redirect additional sunlight toward the planet's surface, particularly targeting the polar regions. These mirrors, potentially spanning several square kilometers, would concentrate solar energy where it's most needed. The increased solar radiation would help melt the carbon dioxide ice at the poles, releasing this greenhouse gas naturally into the Martian atmosphere. Engineers have calculated that a network of well-placed space mirrors could raise local temperatures by several degrees, potentially triggering regional climate changes that could spread globally over time. The concept of asteroid redirection represents a more dramatic approach. By carefully calculating trajectories, scientists have proposed that we could guide ammonia-rich asteroids to impact Mars in controlled locations. These impacts would serve multiple purposes. The kinetic energy would release heat, the ammonia would act as a potent greenhouse gas, and the collision could release subsurface water and minerals. While certainly high risk, this method offers rapid delivery of both heat and necessary atmospheric components. Computer models suggest that a series of carefully orchestrated impacts over several decades could significantly alter the Martian climate system. Nuclear technology offers another powerful heating option. Small nuclear reactors distributed across the Martian surface could create hotspots of warmth that might gradually expand. These power sources would not only provide heat directly, but could also power facilities that produce greenhouse gases or process local resources. Some proposals even suggest using controlled nuclear detonations beneath the surface to release heat and trapped gases simultaneously. Though this approach raises serious concerns about radioactive contamination, the biological approach takes a different angle by using specially engineered extremophile organisms. Scientists have identified microorganisms on Earth that survive in Mars-like conditions, and with genetic modifications, these could potentially thrive on Mars. These organisms would be designed to convert Martian soil compounds into atmospheric gases or dark pigments that absorb more solar radiation. While slower than other methods, this biological transformation would be self-replicating and potentially more sustainable over centuries of development. Developing specialized dark materials to change the planet's albedo, reflectivity, represents another ingenious approach. By covering large areas of the Martian surface with dark, heat-absorbing materials, more solar energy would be captured rather than reflected back into space. These materials could be manufactured from local resources and distributed by autonomous vehicles or aerial systems. As these dark regions warm, they could create local weather patterns that help distribute heat to surrounding areas. One particularly ambitious concept involves the creation of artificial greenhouse domes that would gradually expand and connect. These controlled environments would start small, but prove the concept of warming and atmospheric modification on a local scale before implementing planet-wide solutions. Within these domes, scientists could test various approaches and combinations of techniques to determine the most effective pathways before scaling up. The utilization of Mars' natural methane represents another intriguing possibility. Various observations have detected methane releases on Mars, possibly from geological processes or even potentially from existing microbial life. If these sources could be identified and enhanced, they might provide a natural mechanism for increasing greenhouse gas concentrations without requiring external resources. Most researchers in the field agree that the most practical approach would involve combining several of these methods in a carefully sequenced strategy over many decades or centuries. Initial warming might come from orbital mirrors and artificial greenhouse gases, followed by biological approaches once temperatures reach viable ranges for engineered organisms. The process would require constant monitoring and adjustment based on observed planetary responses. The challenges shouldn't be underestimated. Mars lacks a strong magnetic field to protect any developing atmosphere from being stripped away by solar wind. Any warming strategy would need to account for this by either producing gases faster than they're lost to space or addressing the magnetic field deficiency through artificial means. Additionally, the energy requirements for many of these approaches are enormous, requiring significant advances in space-based power generation and transmission. Warming Mars represents just the first step in a comprehensive terraforming process. While increasing the temperature would make liquid water possible on the surface, creating a breathable atmosphere and establishing ecosystems would require additional massive interventions. Nevertheless, the theoretical frameworks for warming the red planet provide an exciting glimpse into humanity's potential future as a multiplanetary species, applying our understanding of planetary climate systems to the ultimate geoengineering project. Reduction of Venus's dense and toxic atmosphere. When we think about planets that might someday be transformed to support human life, Venus rarely tops the list, and with good reason. Our sister planet presents challenges that make Mars look like a vacation destination in comparison. Beneath its perpetual cloud cover lies an environment of extremes, with the most pressing issue being its incredibly dense and toxic atmosphere. Tackling this atmospheric problem would be the first monumental hurdle in any serious consideration of Venusian terraforming. Venus's atmosphere is a crushing blanket, over 90 times denser than Earth's, composed primarily of carbon dioxide with clouds of sulfuric acid. This atmosphere creates surface pressures equivalent to being about 1 kilometre deep in Earth's oceans and maintains surface temperatures around 465 degrees Celsius, hot enough to melt lead. Any terraforming effort would need to dramatically reduce this atmosphere in both volume and toxicity. One of the most straightforward approaches, conceptually at least, would be the direct removal of atmospheric gases. Enormous processing facilities positioned in Venus's upper atmosphere could separate carbon dioxide molecules and either store the carbon in solid form or convert it into useful materials. The oxygen released could be preserved for later use in creating a more Earth-like atmosphere. While simple in concept, the scale required is mind-boggling. We would need to process over 1 quadrillion tons of carbon dioxide, requiring energy and resources far beyond our current capabilities. A more elegant solution might leverage Venus's natural cloud layer. Some scientists have proposed seeding the upper atmosphere with genetically engineered bacteria or algae that could survive in the less hostile conditions of the upper clouds, where temperatures and pressures are much more Earth-like. These organisms would use photosynthesis to convert carbon dioxide into oxygen while producing organic compounds that would eventually rain down to the surface. This biological approach offers the advantage of being self-replicating, potentially accelerating over time as the organisms multiply. The concept of solar shading represents another critical strategy. By positioning enormous sunshades at the Lagrange point between Venus and the Sun, we could reduce the solar radiation reaching Venus by as much as 20%. This cooling effect would cause the carbon dioxide in the atmosphere to gradually condense and potentially freeze onto the surface, naturally reducing atmospheric pressure. Models suggest that with sufficient shading maintained over centuries, Venus's surface temperature could drop dramatically, making subsequent terraforming steps more feasible. The introduction of hydrogen to the Venusian atmosphere presents a particularly promising chemical approach. Hydrogen would react with carbon dioxide to form water and graphite through various chemical pathways. This would simultaneously reduce the atmospheric carbon dioxide while creating water, solving two terraforming challenges at once. The hydrogen could be harvested from the gas giants or their moons and delivered to Venus using advanced propulsion systems. While enormously challenging in scale, this approach is feasible with known chemistry. Some scientists have proposed using orbital lasers or focused solar energy to excite the upper atmosphere of Venus in controlled patterns, creating pathways for gases to escape into space more easily. This approach would accelerate the natural atmospheric loss that occurs as solar radiation interacts with atmospheric molecules. By carefully targeting specific regions and atmospheric components, we could potentially help Venus shed its excessive atmosphere over centuries, rather than the billions of years this would take naturally. Cooling technologies deployed at massive scales could condense portions of the atmosphere for processing. Initial facilities would need to be heavily shielded against the extreme conditions, but could create atmospheric wells, where local conditions become progressively more manageable as the technology succeeds. These islands of reduced atmospheric pressure could gradually expand, creating footholds for additional technology deployment. The extraction of useful elements from Venus's atmosphere represents an approach that might help fund such an enormous undertaking. The atmosphere contains valuable resources, including carbon, sulfur, and various trace elements that could be harvested for use in space-based construction or returned to Earth. This mining operation could potentially offset some of the immense costs of terraforming while simultaneously serving the primary goal of atmospheric reduction. One particularly ambitious concept involves the creation of enormous floating cities positioned in the more temperate regions of Venus's upper atmosphere. These habitats would serve as both living spaces for researchers and workers, and as processing facilities for atmospheric transformation. At about 50 kilometers above the surface, conditions are surprisingly Earth-like in terms of temperature and pressure, making this region the logical starting point for any Venusian presence. Any serious attempt at transforming Venus would likely employ a multi-phase approach spanning centuries. Initial efforts would focus on reducing temperature and pressure through solar shades and atmospheric processing. Once conditions became less extreme, biological methods could be introduced to accelerate the conversion of carbon dioxide. The final phases would involve the careful introduction of water and nitrogen to create a more Earth-like atmospheric composition. The technical challenges are immense, but so are the potential rewards. A terraformed Venus would offer a planetary surface area nearly equivalent to Earth's, potentially doubling the habitable real estate in our inner solar system. The technologies developed to tackle Venus's hostile atmosphere would also have applications for addressing climate issues on Earth and terraforming other worlds. The transformation of Venus remains one of humanity's greatest potential achievements, not something for the next few decades, but perhaps for the coming centuries as our technological capabilities and understanding of planetary systems continue to advance. While Mars may be our first step in planetary engineering, Venus represents the ultimate challenge and opportunity in our solar system. Beyond modifying the physical conditions of Mars and Venus, the successful terraforming of these planets would require establishing functioning ecosystems. With the atmospheric and temperature conditions moving in the right direction, the next crucial step would involve creating life forms capable of thriving in these still challenging environments. The development of genetically engineered organisms for Mars represents one of the most fascinating aspects of potential terraformation projects. Unlike Venus, Mars already has conditions that, while hostile to most Earth life, could support specially adapted organisms with relatively less atmospheric modification. This biological transformation would begin with the simplest forms of life and gradually increase in complexity. The first pioneers in a Martian ecosystem would almost certainly be modified cyanobacteria. These remarkable microorganisms have several qualities that make them ideal candidates. They can perform photosynthesis, converting carbon dioxide to oxygen. Many strains can fix nitrogen from the atmosphere, and they're already among Earth's most radiation-resistant and hardy life forms. Scientists have identified strains from Antarctica and high-altitude deserts that naturally withstand conditions somewhat similar to Mars. These would serve as the baseline for genetic modifications. The necessary modifications to these bacteria would be extensive. They would need enhanced radiation resistance far beyond what occurs naturally on Earth to withstand the intense ultraviolet and cosmic radiation that reaches the Martian surface. Their cellular machinery would require adjustments to function at much lower temperatures and pressure. They would need modified photosynthetic systems capable of operating efficiently in the dimmer sunlight that reaches Mars, which receives less than half the solar energy that Earth does. Perhaps most challenging would be engineering protection against the perchlorates found in Martian soil, compounds that are toxic to most Earth life. Laboratory work on Earth has already begun creating prototype organisms with some of these adaptations. Research teams have successfully modified cyanobacteria to survive higher radiation doses and to metabolize perchlorates, transforming these toxic compounds into harmless byproducts. These experiments, while preliminary, demonstrate that the concept is feasible with further refinement. Following the establishment of bacterial colonies, the next stage would involve introducing genetically modified lichens and mosses. These symbiotic organisms, partnerships between fungi and algae or bacteria, are nature's pioneers on Earth, capable of colonizing bare rock and beginning the soil creation process. For Mars, they would need similar modifications to the bacteria: radiation resistance, cold tolerance, and the ability to gather sufficient moisture from the thin atmosphere or subsurface ice. The advantage of lichens is their extreme resilience. On Earth, lichens survive in the harshest environments from Antarctica to scorching deserts. Their ability to go dormant when conditions are unfavourable means they could potentially survive the extreme temperature swings on Mars, active during warmer periods and dormant during the coldest times. As these simple organisms begin modifying the surface chemistry and creating primitive soil, the next wave would include engineered plants. These would likely begin with modified versions of Earth's most resilient plants, species like Arctic moss campion, desert succulents, and certain grasses that tolerate extreme conditions. Genetic modifications would include specialized root systems to extract water from near-frozen soil, enhanced photosynthetic pigments to capture more energy from the weaker Martian sunlight, and cellular adaptations to prevent freezing. One of the most promising approaches involves creating plants with entirely new metabolic pathways not found in nature. Scientists have proposed plants that could photosynthesize using hydrogen peroxide as an intermediate rather than water, which would be better suited to the Martian environment. Others have suggested plants that incorporate perchlorate processing genes from specialized bacteria, turning Mars's toxins into plant nutrients. The soil building process would be crucial for any plant life. On Earth, soil development can take thousands of years, but engineered microorganisms could potentially accelerate this process. Specially designed fungi and bacteria would break down Martian regolith, releasing trapped nutrients and creating the complex organic structures that make soil fertile. Perhaps the most complex challenge would be creating complete, functional microbiomes, the interdependent communities of microorganisms that make ecosystems work. Natural Earth ecosystems rely on thousands of microbial species performing specialized roles in nutrient cycling. For Mars, scientists would need to design simplified but functional versions of these relationships, ensuring that critical processes like nitrogen fixation, carbon cycling, and decomposition all function properly. The risks of this biological engineering must be carefully managed. Any organisms released on Mars would need extensive testing in Mars simulating chambers on Earth, and then in contained facilities on Mars itself before being released into the environment. Researchers would need to be certain these engineered life forms couldn't become invasive or disruptive if Martian conditions change, or if native Martian microbial life, should it exist, were encountered. The gradual introduction of increasingly complex organisms would follow ecological succession principles similar to those on Earth, but deliberately guided and accelerated. Each new species would be introduced only after its predecessors had sufficiently modified the environment to support it. This process, while potentially taking centuries, would ultimately lead to self-sustaining ecosystems capable of maintaining atmospheric transformations without constant human intervention. The creation of these pioneer ecosystems represents a middle ground between engineering planetary conditions and adapting ourselves to alien environments, using modified biology to transform worlds in ways that machines alone cannot. While the genetic approaches to building Martian ecosystems represent one crucial aspect of terraforming, equally important is determining the appropriate time frame for planetary transformation. The debate between gradual terraforming spanning millennia versus rapid transformation completed in centuries hinges on fundamental questions about technology, resources, and risk management. The gradual approach to terraforming represents the more conservative path. This strategy would involve incremental changes to planetary conditions over thousands of years, allowing natural feedback systems to stabilize between human interventions. Proponents argue that this approach carries significantly lower risks of catastrophic, unintended consequences. By making changes slowly, scientists could carefully monitor planetary responses, adjusting their techniques based on real data rather than theoretical models. A millennia-long project would begin with modest interventions, perhaps the introduction of heat-trapping gases and radiation-resistant microorganisms on Mars, or the initial deployment of atmospheric processing stations on Venus. Each step would be followed by decades or even centuries of observation before proceeding to the next phase. This extended timeline allows planetary systems to reach new equilibria naturally, potentially revealing issues that rapid approaches might miss. The practical advantages of gradual terraforming extend beyond safety. The energy requirements would be spread across many generations, making the project more economically feasible. Current estimates suggest that rapidly warming Mars would require energy equivalent to thousands of nuclear power plants operating continuously for centuries, an investment beyond our current global capacity. By spreading these energy needs across longer timeframes, each generation would bear a more manageable portion of the total cost. Additionally, the gradual approach allows for technological development alongside planetary transformation. Technologies that seem impossible or prohibitively expensive today might become routine in a few centuries. By planning for a longer timeline, terraforming projects could incorporate these future innovations rather than being locked into current technological limitations. Perhaps most significantly, gradual terraforming would allow human societies and the emerging planetary environments to co-evolve. Communities established in early habitats would develop cultural adaptations to their partially transformed worlds, potentially creating unique civilizations with deeper connections to their adopted planets. These communities would develop specialized knowledge about their changing environments, passing this expertise through generations. The alternative approach, rapid planetary transformation, offers its own compelling advantages. With sufficient technological advancement, particularly in fields like nanotechnology, robotics, and fusion energy, the time frame for terraforming could potentially be compressed into several centuries rather than millennia. This accelerated approach would employ far more intensive intervention, using technologies that might seem almost theoretical from our current perspective. Rapid terraforming would likely rely heavily on self-replicating systems. Imagine swarms of specialized robots manufacturing greenhouse gases directly from Martian regolith, or fleets of atmosphere processing stations reproducing themselves across Venus's clouds. Once initiated, these systems could grow exponentially, transforming planetary conditions at rates impossible with more controlled approaches. The energy requirements for rapid transformation would be enormous, but might be met through advanced power generation. Massive solar arrays in orbit around the target planet could capture and direct energy far more efficiently than surface-based systems. Fusion power, if mastered, could provide the nearly limitless energy needed for planetary engineering on accelerated timescales. Computer models of planetary systems have suggested that certain tipping points exist where relatively small interventions can trigger much larger changes, similar to how releasing enough greenhouse gases on Earth can trigger ice cap melting, which then accelerates warming. Rapid terraforming strategies aim to identify and target these leverage points, creating cascading positive changes throughout the planetary system. The most practical approach might combine elements of both strategies. Many scientists propose a hybrid model featuring intensive phases of transformation followed by longer periods of stabilization and observation. This would allow for faster progress than purely gradual approaches while maintaining sufficient caution to prevent catastrophic failures. For Mars, such a hybrid approach might begin with an intensive century of greenhouse gas production and orbital mirror deployment to raise temperatures above the freezing point of water, followed by several centuries of controlled biological transformation to build oxygen levels and create functional soils. For Venus, an initial period of aggressive atmospheric extraction might be followed by a longer cooling phase as the transformed surface adjusts to its new conditions. The question of timescale ultimately reflects deeper questions about human patience and vision. Rapid transformation appeals to our desire for immediate results, potentially allowing current generations to see significant progress within their lifetimes. Gradual approaches, while less immediately gratifying, might produce more stable and sustainable outcomes, planets that remain habitable for millions of years rather than requiring constant maintenance. The economic and social implications of these different timeframes cannot be overlooked. Rapid terraforming would require massive resource mobilization over shorter periods, likely demanding unprecedented global cooperation or the emergence of enormously powerful entities capable of planetary-scale projects. Gradual approaches, while requiring commitment over longer timeframes than human institutions typically maintain, would distribute costs and benefits across many generations. These different visions for planetary transformation timeframes represent not just technical disagreements, but fundamentally different philosophies about humanity's relationship with time and the cosmos. As our technological capabilities advance, the theoretical debates may soon give way to practical decisions as the first serious terraforming initiatives move from speculation to planning. Whether using a rapid or gradual approach to terraformation, one fundamental challenge remains constant: the enormous resource requirements needed to transform an entire planet. The success of any terraforming project would depend not only on the technologies employed, but also on careful management of the materials needed over centuries or millennia of sustained effort. Resource management for sustainable terraforming represents perhaps the most practical challenge for any planetary transformation effort. Unlike most human projects that can be supplied from Earth's abundant resources, terraforming would need to operate largely on locally sourced materials due to the prohibitive costs of transporting large masses between planets. This necessity for in situ resource utilization would shape every aspect of how terraforming projects unfold. The most abundant resources on Mars and Venus are found in their soils, atmospheres, and potentially subsurface deposits. Martian regolith contains useful minerals including iron oxides, silicates, and various salts, while the atmosphere, though thin, provides carbon dioxide that could be processed into other compounds. Venus offers an atmosphere rich in carbon, oxygen, and sulfur compounds that could be harvested and transformed. However, both planets lack certain elements crucial for Earth-like ecosystems, particularly nitrogen and phosphorus in accessible forms. This elemental scarcity presents a significant challenge. Nitrogen, essential for all known life as a component of proteins and DNA, exists on Mars only in trace atmospheric amounts and potentially in subsurface nitrate deposits. On Venus, nitrogen is present in the atmosphere but at lower concentrations than carbon dioxide. Phosphorus, critical for DNA and energy transfer in organisms, would need to be extracted from planetary crustal rocks through chemical or biological processing. Creating functional ecosystems would require carefully managing these scarce elements to prevent losses and ensure they cycle efficiently through the developing biosphere. Asteroid mining would likely become an essential component of terraforming resource strategies. Near-Earth asteroids and objects in the main asteroid belt contain materials that could supplement planetary deficiencies. Carbonaceous asteroids often contain water ice, carbon compounds, and nitrogen, while metallic asteroids provide metals and rarer elements. The development of efficient asteroid capture and processing technologies would be a prerequisite for serious terraforming efforts. Water management would be particularly crucial for Martian terraforming. While evidence suggests substantial subsurface ice deposits exist on Mars, extracting this water and preventing its loss to space once vaporized would require careful engineering. Initial settlement and terraforming activities would need to operate with closed-loop water recycling systems far more efficient than anything currently used on Earth. Every molecule of water would be tracked and conserved until the planetary hydrological cycle became self-sustaining, potentially centuries into the terraforming process. Energy resources present another fundamental consideration. The massive energy requirements for planetary engineering would likely be met through a combination of nuclear and solar power. Space-based solar arrays could harvest energy more efficiently than surface installations, especially on Venus, where the dense atmosphere would limit surface solar collection. For Mars, with its greater distance from the Sun, nuclear power might play a more dominant role in early transformation stages. The development of fusion power would dramatically improve the feasibility of large-scale terraforming by providing the sustained high-energy output needed for atmospheric processing and other energy-intensive operations. The concept of closed-loop systems would be central to sustainable terraforming. Unlike Earth's development, where resources could be used and discarded as new frontiers opened, terraforming would require approaching planets as closed systems where every element must be carefully tracked and recycled. This would necessitate advanced recycling technologies capable of capturing and reusing nearly 100% of materials from any industrial or biological process. Technologies being developed for space stations and potential lunar bases offer early prototypes for these systems, but terraforming would require scaling these approaches to planetary dimensions. Manufacturing infrastructure in situ would dramatically reduce the need for Earth-launched supplies. Advanced 3D printing using local materials could produce everything from habitat structures to machinery components. Biological manufacturing, using engineered organisms to create materials and chemicals, could provide another resource-efficient production method particularly suited to the limited environments of partially terraformed planets. These local manufacturing capabilities would need to be established early in any terraformation process, creating a foundation for self-sufficiency. Strategic resource stockpiling would be necessary for elements that remain rare despite all recycling efforts. Nitrogen, phosphorus, and certain trace metals would likely be collected and stored in accessible forms to support future ecosystem expansion. These strategic reserves would function similarly to Earth's seed banks, preserving essential materials for future use as the terraforming project progresses through its centuries-long development. Perhaps most challenging would be creating and maintaining the social and institutional systems needed for multi-generational resource management. Human institutions rarely plan beyond decades, yet terraforming resources would need management across centuries. This would require developing new governance structures specifically designed for extremely long-term projects, possibly incorporating artificial intelligence systems to maintain consistency in resource allocation policies across generations. The economics of terraforming resource management would differ fundamentally from traditional economic models, with timeframes extending centuries into the future. Traditional discount rates that minimize the value of distant benefits would be inappropriate. New economic frameworks would be needed that properly value long-term sustainability and recognize the true costs and benefits of planetary transformation across multiple human lifespans. Education and knowledge preservation about resource management would become crucial. Each generation of terraforming engineers and administrators would need to understand not just current resource utilization, but the complete history of what had been done previously and why. This would require developing knowledge preservation systems more durable and accessible than anything in human history, ensuring that critical information about resource distributions and management strategies survives across centuries of continued effort. The resource management strategies developed for terraforming projects would likely yield valuable insights for sustainability on Earth as well. The necessity of approaching a planet as a closed system with careful tracking of material flows mirrors the challenges our home planet now faces with resource depletion and pollution. Terraforming research might paradoxically help us better manage Earth's resources by forcing the development of more sophisticated models for planetary material cycles. The massive scale of terraforming raises profound ethical questions that extend far beyond technical feasibility. As humanity contemplates making permanent changes to other worlds, we face dilemmas without precedent in our species' history. These ethical considerations may ultimately prove more challenging than the engineering problems of planetary transformation. The most fundamental ethical question concerns humanity's right to transform other planets. Unlike Earth, where human modifications of the environment occurred gradually and often without understanding the consequences, terraforming would represent a deliberate choice to permanently alter entire worlds. This level of intentional change forces us to confront questions about whether pristine planetary environments have intrinsic value that should be preserved, regardless of their utility to humans. The possible presence of indigenous Martian or Venusian life, even in microbial form, dramatically complicates the ethical landscape. Despite decades of searching, we have not yet definitively determined whether life exists or ever existed on either planet. Mars, with evidence of past liquid water and organic molecules in its soil, remains a particularly plausible habitat for simple life forms that might exist in subsurface environments protected from surface radiation. Recent detection of phosphine in Venus's atmosphere has raised intriguing possibilities about potential microbial life in the cloud layers. If indigenous life were discovered on either planet, even in the simplest forms, terraforming would risk biological contamination that could lead to extinction of these unique life forms. The ethical weight of potentially eliminating the only known example of life that evolved independently from Earth would be enormous. Some scientists argue that even the possibility of such life justifies taking a highly precautionary approach, thoroughly exploring Mars and Venus for signs of life before considering any irreversible changes to their environments. The question of who decides whether and how to terraform raises equally challenging issues of governance and representation. Should such monumental decisions require global consensus on Earth? What about considering the interests of future generations who would live on these transformed worlds but have no voice in present deliberations? The unprecedented timescales of terraforming projects mean that decisions made today would constrain the options available to humans living centuries from now, raising questions about intergenerational justice. The enormous resources required for terraforming also create ethical dilemmas about prioritization. With limited global resources, investment in planetary transformation would necessarily reduce what's available for addressing immediate human needs on Earth. Advocates argue that terraforming represents a crucial investment in humanity's long-term future, providing insurance against Earth-based catastrophes and opening new frontiers for human development. Critics counter that these resources could better serve humanity by addressing present challenges like poverty, disease, and environmental degradation on our home planet. Cultural and social considerations extend beyond resource allocation. Different human cultures and traditions hold varying perspectives on humanity's relationship with nature and our role in shaping environments. Some religious and philosophical traditions emphasize stewardship and minimal intervention, while others place greater emphasis on human creativity and transformation of environments. Terraforming decisions would inevitably privilege some of these worldviews over others, raising questions about cultural justice and respect for diverse perspectives. The irreversibility of terraforming decisions adds weight to these ethical considerations. Unlike many human activities whose effects can be mitigated or reversed, changing the fundamental character of an entire planet creates a one-way path. Once initiated at scale, terraforming processes would likely be impossible to fully reverse, meaning that mistakes or unintended consequences could persist for geological timescales. This permanence demands extraordinary care in decision-making, with greater emphasis on precautionary principles than is typical in human enterprises. Conservation ethics developed for Earth environments take new forms when applied to other planets. On Earth, conservation often focuses on preserving biodiversity and ecosystem services. For lifeless or nearly lifeless planets, conservation would instead concern geological, chemical, and atmospheric features that have scientific value or represent unique planetary histories. The ancient river valleys and polar ice caps of Mars, for instance, contain irreplaceable records of the planet's development that would be lost in terraforming. Some philosophers and scientists have proposed middle ground approaches that might partially address these ethical concerns. Para-terraforming, creating localized habitable environments while leaving most of a planet in its natural state, could allow human settlement while preserving much of the original planetary character. Similarly, designating certain regions as scientific preserves where no terraforming activities would occur might balance human development needs with conservation values. The development of ethical frameworks specifically for planetary modification has only recently begun. Existing principles like those governing scientific research in Antarctica or guidelines for planetary protection in space exploration provide starting points, but are insufficient for the scale and permanence of terraforming decisions. New ethical paradigms that can adequately address the unique moral questions of planetary transformation will need development alongside the technical capabilities that make terraforming possible. These ethical considerations should not be viewed merely as obstacles to terraforming, but as essential components of responsible decision-making about humanity's role in the solar system. Just as environmental ethics has matured to inform Earth-based development, space ethics must evolve to guide our species as our technological reach extends to other worlds. The answers we develop to these profound questions will shape not just the physical features of other planets, but our own identity as a spacefaring civilization. While the ethical debates about terraforming continue, scientists and engineers have been developing increasingly detailed timelines and technological solutions for the practical aspects of planetary transformation. Understanding realistic timeframes helps put the enormous challenge in perspective, while highlighting the incremental achievements that would mark progress along the way. Realistic timelines for terraforming must account for both technological limitations and the fundamental physical processes involved in planetary change. Unlike science fiction depictions where worlds transform within human lifespans, actual terraforming would unfold across multiple generations, with distinct phases of development leading toward different different levels of habitability. The creation of localized habitable environments represents the first achievable milestone in any terraforming project. Using near-future technology, enclosed habitats with controlled atmospheres could be established on Mars within the next 50 to 100 years. These initial settlements would rely heavily on Earth supplies while developing local resource utilization. While not true terraforming, these outposts would establish the human presence and infrastructure needed for larger-scale planetary modification. The first phase of actual terraforming would focus on creating what scientists call para-terraformed environments, partially enclosed regional ecosystems with modified conditions. On Mars, this might involve transparent domes covering several square kilometers, large enough to develop functional mini-atmospheres and support small-scale agriculture. These intermediate habitats could be achievable within 1 to 2 centuries, using materials mostly sourced from Mars itself. They would serve as testing grounds for biological systems and atmospheric manipulation techniques, while providing expanding human habitation. True planetary transformation would begin with atmospheric modification at global scales. For Mars, models suggest that raising the atmospheric pressure and temperature to support hardy plant life outside enclosed structures would require between 500 and 1,000 years of concentrated effort. This phase would involve massive greenhouse gas production, potentially using automated factories scattered across the planet's surface. During this period, the Martian atmosphere would remain unbreathable for humans, but might reach a point where pressure suits rather than full-pressure habitats would suffice for human activity outdoors. The development of a breathable atmosphere represents a much longer-term goal. Even with the most optimistic technological projections, generating sufficient oxygen through both mechanical and biological processes would likely require between 2,000 and 5,000 years. This extended time frame reflects the sheer volume of gas needed. Earth's atmosphere contains approximately 1 quadrillion tons of oxygen, a quantity that simply cannot be generated quickly even with highly advanced technology. Water cycle development would progress alongside atmospheric changes. Initially, localized melting of subsurface ice deposits would create isolated habitable regions. The establishment of a global hydrological cycle with self-sustaining weather patterns would take significantly longer, potentially between 1 and 200 years, 1,000 and 3,000 years, depending on the amount of water available in Martian polar caps and subsurface reservoirs. The final phase, creating self-sustaining global ecosystems with biodiversity approaching Earth's, represents the most distant goal, potentially requiring 10,000 years or more of continuous effort. This extended time frame reflects not just technological limitations, but the time needed for ecological succession and evolution to create stable, interconnected systems of organisms adapted to Martian conditions. For Venus, the timelines would be even longer. The initial reduction of its crushing atmosphere might take 1,000 to 2,000 years using the most advanced proposed methods. Creating surface conditions where humans could work with minimal protection might require an additional 2,000 to 4,000 years of sustained effort. A fully Earth-like Venus represents an even more distant possibility than a transformed Mars, potentially requiring 15,000 to 20,000 years, 1,000 years of directed development. These extended timeframes highlight an important truth about terraforming. Many generations would live and work on planets in transitional states. Rather than seeing this as a disadvantage, terraforming planners envision a continuous process where each generation inhabits a slightly improved version of the planet while working toward long-term goals. Human societies would adapt to these transitional environments, potentially developing unique cultures and technologies suited to their partially terraformed worlds. The most realistic approaches recognize that terraforming would not proceed at a constant pace. Periods of rapid change might follow technological breakthroughs or the reaching of environmental tipping points. These would likely alternate with plateaus where progress slows as new equilibriums are reached and new challenges emerge. The overall trajectory would resemble less a smooth curve and more a series of steps toward increased habitability. It's worth noting that these timelines assume continuous human commitment to the terraforming project. Historical experience suggests that maintaining societal focus on extremely long-term goals presents its own challenges. Political systems, economic priorities, and cultural values change significantly over centuries. Terraforming projects would need to be structured to withstand these social changes, perhaps through institutional arrangements specifically designed for multi-generational continuity. The creation of these detailed, multi-phase timelines serves a practical purpose beyond mere planning. By breaking down the intimidating prospect of planetary transformation into discrete, achievable milestones, scientists make the concept more accessible to both public understanding and political support. Each successful phase would demonstrate progress and build momentum for continued investment in the longer-term vision. Technological development on Earth would almost certainly accelerate some aspects of these timelines. Major breakthroughs in fields like nanotechnology, biotechnology, or fusion power could potentially compress certain phases significantly. However, some aspects of planetary development simply cannot be rushed. The establishment of soil ecosystems, the stabilization of atmospheric cycles, and the evolution of adapted organisms all require time for natural processes to unfold, regardless of technological intervention. Perhaps the most important aspect of realistic terraforming timelines is their emphasis on patience and long-term thinking. Unlike most human endeavors, terraforming would require planning and commitment on timescales more commonly associated with geological processes than human projects. This unprecedented temporal scope challenges our species to develop new approaches to intergenerational cooperation and responsibility. While atmospheric composition and temperature receive much attention in terraforming discussions, Mars presents another critical challenge: its lack of a protective magnetic field. This absence leaves the Martian surface exposed to harmful solar radiation and would cause any newly developed atmosphere to be gradually stripped away by solar wind. Developing technologies to create artificial magnetic fields thus represents a fundamental requirement for sustainable terraformation. Mars once possessed a strong magnetic field similar to Earth's, generated by the movement of molten material in its core. This field protected an earlier, thicker Martian atmosphere and potentially allowed surface water to exist. However, approximately 4 billion years ago, the Martian core cooled and solidified, shutting down this natural protection. Any terraforming effort would need to compensate for this loss to prevent solar wind from gradually eroding a rebuilt atmosphere back to its current tenuous state. The most straightforward approach to this challenge involves placing a powerful magnetic dipole at the Mars-Sun L1 Lagrange point, a position where the gravitational forces of the two bodies balance each other. From this location, approximately 1 million kilometers sunward of Mars, the device would create a magnetic field that would deflect incoming solar particles around the planet rather than allowing them to strike the atmosphere directly. NASA scientists have conducted preliminary studies of this concept, determining that a magnet with a strength of 1 to 2 Tesla, comparable to modern medical MRI machines but covering a much larger area, could generate a protective bubble encompassing the entire planet. While the engineering challenges are significant, the underlying physics is well understood. The device would likely use superconducting materials to generate its field while requiring substantial power sources, possibly large solar arrays. The advantage of this approach is its efficiency. A single well-placed shield could protect the entire planet while requiring less total energy than multiple surface-based solutions. Models suggest that once in place, such a shield could reduce atmospheric loss by more than 90%, allowing natural processes to begin rebuilding the Martian atmosphere, rather than seeing new gases constantly stripped away to space. An alternative approach involves a constellation of orbiting satellites carrying powerful electromagnets. These satellites, distributed in Martian orbit, would create overlapping protective fields that together would shield the planet. This distributed system might offer greater redundancy than a single shield and could be deployed incrementally, with protection increasing as more satellites join the network. The energy requirements would be substantial, likely requiring each satellite to carry nuclear power sources or extensive solar arrays. For more localized protection, scientists have proposed creating magnetized domes over specific settlement areas. These smaller shields wouldn't protect the entire planet, but could create safe zones for initial human habitation and early terraforming experiments. The technology for these regional shields would be similar to that used in fusion research facilities on Earth, though scaled up significantly and adapted for the Martian environment. A more speculative approach involves attempts to restart Mars's internal dynamo. This would require heating portions of the Martian core back to a liquid state and inducing movement to generate a field naturally, as occurs on Earth. While theoretically possible, this approach represents by far the most energy-intensive and technologically challenging option. It might involve drilling deep into the Martian crust and placing nuclear devices or other heating technologies to melt portions of the subsurface. Some researchers have suggested using natural magnetic materials already present in the Martian crust. Mars has regions with residual magnetism locked into iron-rich minerals. By strategically heating these areas, it might be possible to enhance their magnetic properties and create stronger local fields. While insufficient for global protection, this approach might supplement other technologies in a layered defense strategy. The development of artificial magnetic field technology would progress alongside other terraforming efforts rather than preceding them. Initial atmospheric thickening would likely begin under conditions of continued solar erosion, with the understanding that some percentage of newly generated gases would be lost to space. The implementation of magnetic protection would become increasingly crucial as the atmosphere developed to prevent this continuous leakage from undermining terraforming progress. The energy requirements for maintaining artificial magnetic fields would need to be factored into the overall resource budget for terraforming. Depending on the approach chosen, magnetic protection could consume between 5 and 20% of all energy produced by a developing Martian civilization. This substantial investment would be justified by the alternative, continuously replacing atmospheric gases lost to space, which would require even greater long-term energy expenditure. The technologies developed for Martian magnetic protection would have applications beyond terraforming. The same principles could protect human space travelers from radiation during interplanetary journeys or shield space stations and lunar bases. The materials science advances needed for large-scale superconducting magnets would likely find applications in energy storage, transportation, and computing on Earth and throughout the solar system. Perhaps most intriguingly, the development of artificial magnetospheres might eventually allow human habitation in regions of the solar system previously considered too radiation exposed for long-term settlement. The moons of Jupiter, for instance, lie within the giant planet's intense radiation belts. Local magnetic shields based on technology developed for Mars could potentially make these otherwise promising locations viable for human habitation. The creation of artificial magnetic fields represents one of the clearest examples of how terraforming would require humans to replace or supplement fundamental planetary processes. Unlike most Earth-based geoengineering, which works with existing planetary systems, Martian magnetic protection would require humanity to recreate a core planetary function lost billions of years ago, a level of planetary engineering unprecedented in human history. While creating magnetic shields and modifying planetary atmospheres represent enormous engineering challenges, perhaps the most unpredictable aspects of terraforming would involve the ecological systems introduced to transformed planets. The history of Earth's own ecosystem interventions suggests that even carefully planned biological introductions can lead to unexpected and sometimes problematic outcomes when implemented at planetary scales. The potential for unforeseen ecological consequences in terraforming projects stems from the immense complexity of biological systems. Even the simplest Earth ecosystems involve thousands of species interacting through elaborate food webs, chemical cycles, and competitive relationships. When attempting to create new ecosystems on other planets, scientists would face the challenge of reproducing these intricate relationships in environments fundamentally different from those that shaped Earth's life. One of the most significant risks involves population dynamics of introduced species. On Earth, when organisms are introduced to new environments without their natural predators or competitors, they frequently undergo population explosions followed by devastating crashes. The classic example of rabbits introduced to Australia demonstrates how a seemingly harmless addition can transform into an ecological disaster when normal population controls are absent. In a terraforming context, certain microbes or plants engineered to survive harsh Martian conditions might reproduce explosively once environmental modifications improve conditions, potentially outcompeting other introduced species or consuming resources needed for subsequent stages of ecological development. The behavior of genetically engineered organisms presents particular concerns. The modified microbes, plants, and eventually animals developed for terraforming would would likely contain significant genetic changes to help them survive alien conditions, enhanced radiation resistance, different atmospheric requirements, or modified temperature tolerances. These changes might have unforeseen effects on other traits, potentially altering growth rates, reproductive strategies, or chemical processes in ways that laboratory testing on Earth couldn't fully predict. The ecological consequences of these altered traits might only become apparent decades or centuries after introduction, when removing problematic organisms would be extremely difficult. Biogeochemical cycles, the movement of essential elements like carbon, nitrogen, and phosphorus through living and non-living systems, present another area for potential unexpected consequences. Earth's cycles developed over billions of years of evolution, creating balanced flows that maintain relatively stable conditions. Attempts to replicate these cycles on Mars or Venus would involve introducing organisms to perform specific functions like nitrogen fixation or carbon sequestration. If these organisms perform these functions too efficiently or not efficiently enough, nutrient imbalances could develop, potentially leading to algal blooms in newly formed water bodies or nutrient deficiencies that stunt the development of more complex plant life. The introduction of liquid water to Mars could activate currently dormant microorganisms that might have persisted in subsurface environments. While most scientists believe Mars is currently sterile, the possibility of indigenous microbial life, perhaps in metabolically inactive states, cannot be completely ruled out. If such organisms exist, their interactions with introduced Earth microbes would be completely unpredictable, potentially resulting in competitive exclusion of terraforming organisms, or even the development of novel pathogens through genetic exchange between Earth and Martian life forms. Climate feedbacks represent some of the most concerning potential consequences. Earth's climate history shows that small changes can trigger feedback loops that dramatically amplify initial effects. For example, warming that releases methane from permafrost leads to more warming, which releases more methane. In terraforming scenarios, similar positive feedback loops could develop in unexpected ways. The introduction of dark-coloured algae to Mars, intended to absorb sunlight and warm the surface, might spread more rapidly than anticipated, creating a warming effect that exceeds models and triggers further changes like rapid ice cap melting or atmospheric composition shifts beyond desired parameters. Soil development processes might follow unexpected pathways on other planets. The creation of fertile soil from raw regolith involves complex interactions between minerals, organic matter, and living organisms. On Mars, the presence of perchlorates and other toxic compounds in the soil could lead to unusual decomposition processes or the accumulation of harmful substances in developing food chains. Plants engineered to tolerate these compounds might inadvertently concentrate them, creating toxic hotspots in the developing ecosystem. The timescales involved in terraforming would themselves contribute to unpredictability. Earth's ecosystems have had millions of years to develop complex resilience mechanisms through natural selection. Terraformed ecosystems would be expected to develop similar resilience within centuries or millennia, an evolutionary blink of an eye. This compressed timeline increases the risk of system-wide instabilities or collapses when faced with disturbances like solar flares, dust storms, or disease outbreaks. Microbial evolution presents particular challenges due to rapid generation times and genetic adaptability. Bacteria introduced early in terraforming might evolve in unexpected directions over centuries of adaptation to their new planetary home. Some might develop metabolic pathways that produce harmful byproducts or consume resources intended for other organisms. The potential for engineered genes to transfer between species through horizontal gene transfer could lead to the emergence of novel organisms with unpredictable ecological impacts. Scientists planning terraforming efforts would need to implement extensive monitoring systems and maintain the capability to intervene when unforeseen consequences emerge. This would likely involve developing ecological firebreaks, mechanisms to isolate and contain problematic organisms or processes before they spread planet-wide. Maintaining genetic libraries of all introduced species would allow for the development of targeted countermeasures if certain organisms became problematic. The development of self-limiting genetic modifications, where organisms cannot reproduce beyond certain generations without specific interventions, might provide additional safety measures. Despite these challenges, the history of ecological restoration on Earth demonstrates that complex, functional ecosystems can develop even from severely degraded starting points, given sufficient time and appropriate foundational species. The unforeseen consequences of terraforming would represent not just risks to be mitigated, but also opportunities for learning about ecological principles under entirely new conditions. The development of terraformed ecosystems would inevitably include setbacks and surprises, requiring an adaptive management approach that treats planetary development as an ongoing experiment requiring constant adjustment rather than a predetermined path with a fixed endpoint. While addressing the biological challenges of terraforming, engineers and scientists would simultaneously face the practical question of where to obtain the raw materials needed for planetary transformation. The most promising solution lies not on the planets themselves, but in the smaller bodies of our solar system. Asteroids and comets represent vast, accessible reservoirs of the very resources most needed for terraforming projects. The utilization of asteroids and comets as terraforming resources would build upon technologies initially developed for space mining operations. These small bodies contain water, carbon compounds, metals, and volatiles in concentrations often higher than found on terrestrial planets, and in forms that are frequently easier to access since they lack the strong gravity wells that make resource extraction on planets so energy-intensive. Water-rich comets represent perhaps the most valuable terraforming resource, particularly for Mars. A single medium-sized comet might contain billions of tons of water ice, enough to create small seas on the Martian surface. Beyond simply providing water, cometary impacts would deliver energy that could be harnessed for atmospheric heating, along with valuable carbon compounds and nitrogen that would be essential for developing biological systems. The Kuiper Belt and Oort cloud contain trillions of such objects, representing an essentially unlimited supply of these critical volatiles. The controlled delivery of cometary material would require technologies far beyond our current capabilities, but within the realm of physical possibility. Rather than directing entire comets to impact planets, which would risk catastrophic consequences, terraforming engineers would likely develop methods to capture comets in distant solar orbits, process them into smaller packages, and deliver these materials precisely where needed. This approach would allow for careful control over the quantity and composition of delivered materials while minimizing impact risks. Carbonaceous asteroids offer another crucial resource category. These dark, carbon-rich objects often contain significant percentages of water bound in clay minerals, along with complex organic compounds that could provide the chemical building blocks for early biological systems. The carbon could be processed to create greenhouse gases for atmospheric development or used as raw material for manufactured infrastructure. Some carbonaceous asteroids also contain significant amounts of phosphorus and nitrogen compounds, elements that would be essential for developing functional ecosystems but might be limited on Mars and Venus. Metallic asteroids would provide the raw materials needed for construction of terraforming infrastructure. Iron, nickel, platinum group metals, and other elements found in high concentrations in these bodies would be used to build everything from atmospheric processing plants to orbital mirrors and magnetic field generators. The utilization of these in-space resources would drastically reduce the amount of material that would need to be launched from Earth, making terraforming economically feasible in ways that Earth-supplied missions never could be. The asteroid belt between Mars and Jupiter contains enough material to completely transform both Mars and Venus many times over. A single kilometer-sized carbonaceous asteroid contains more water than would be needed to fill thousands of Olympic-sized swimming pools, while the total water content of the belt likely exceeds the volume of Earth's oceans. The technology to identify, reach, and process these resources is already in early development by private space companies and space agencies considering asteroid mining for more immediate economic returns. For Venus, asteroids could serve additional specialized functions. Water-rich asteroids directed into the Venusian atmosphere could help reduce atmospheric carbon dioxide through chemical reactions, potentially binding it in stable mineral forms. Metallic asteroids processed into fine dust and suspended in the upper Venusian atmosphere could create reflective layers that reduce surface temperatures by blocking incoming solar radiation. Processed asteroid materials could also be used to construct the floating habitats that would likely represent humanity's first footholds in the Venusian environment. The development development of a solar system-wide resource utilization infrastructure would likely precede and then develop alongside terraforming efforts. Initial asteroid mining would target high-value metals for return to Earth markets, building the technological capabilities and economic incentives for more ambitious operations. As these capabilities mature, the focus would expand to include the volatile rich objects more valuable for terraforming but less immediately profitable in conventional economic terms. The transportation infrastructure needed to move asteroidal and cometary materials would itself represent one of humanity's greatest engineering achievements. Various proposals include mass drivers that would electromagnetically launch processed materials toward target planets, solar-powered ion engines that would slowly but efficiently redirect entire small asteroids, and processing facilities that would convert ice into water vapor jets used as low-energy propulsion. The development of these systems would create a transportation network throughout the inner solar system, effectively creating shipping lanes between resource sources and the planets targeted for transformation. The economics of asteroid utilization for terraforming would differ fundamentally from traditional resource extraction. While initial asteroid mining would focus on rare metals with immediate market value, terraforming resources like water ice and carbon compounds have their value primarily in their location. Resources already in space are inherently more valuable for space development than similar materials that would need to be launched from Earth at enormous expense. This creates economic incentives that align differently from traditional resource markets, potentially favouring long-term development over immediate profitability. The legal framework for asteroid utilization remains underdeveloped. The Outer Space Treaty establishes that no nation can claim sovereignty over celestial bodies, but it doesn't clearly address resource utilization rights. New international agreements would likely be needed to establish orderly development of these resources, particularly when considering projects as consequential as planetary terraforming. These agreements would need to balance incentives for development with protections against monopolization of crucial resources by single entities or nations. The asteroid and comet utilization technologies developed for terraforming would have applications well beyond planetary transformation. The same capabilities would enable construction of large-scale habitats throughout the solar system, resource extraction for Earth's growing population, and eventually the infrastructure needed for humanity to extend its reach to the outer planets and beyond. In this way, terraforming projects would serve as both beneficiaries of and catalysts for humanity's development as a truly spacefaring civilization. The development of space-based resource utilization networks would provide the raw materials for terraforming, but the true challenge of creating habitable worlds lies in establishing the complex biogeochemical cycles that make Earth's ecosystem function. These interconnected systems, the continuous movement of essential elements between living organisms, the atmosphere, oceans and soil, represent some of the most intricate aspects of a living planet and cannot simply be built as one would construct physical infrastructure. The nitrogen cycle exemplifies the complexity involved in establishing these planetary systems. On Earth, atmospheric nitrogen gas makes up 78% of our atmosphere, yet most organisms cannot use this form directly. Instead, specialized bacteria convert atmospheric nitrogen into ammonia and nitrates that plants can absorb, a process called nitrogen fixation. Other microorganisms later convert these compounds back to atmospheric nitrogen, completing the cycle. For a terraformed Mars or Venus, scientists would need to carefully engineer this entire cycle from scratch. Creating a functional nitrogen cycle would begin with introducing specialized nitrogen-fixing bacteria in controlled environments. These might include both free-living species, like Azotobacter, and symbiotic organisms, like Rhizobium, that form partnerships with plant roots. However, simply introducing these organisms wouldn't be sufficient. The bacteria would need extensive genetic modifications to function in the higher radiation, different soil chemistry, and atmospheric composition of a partially terraformed planet. The balanced introduction of denitrifying bacteria would be equally important. These organisms convert nitrates back to atmospheric nitrogen, preventing dangerous accumulation of nitrogen compounds in soil and water. Without this counterbalance, nitrates could build up to toxic levels or leach into waterways, causing algal blooms and ecosystem disruption similar to agricultural runoff problems on Earth. The careful calibration of these opposing processes, nitrogen fixation and denitrification, would require decades of monitoring and adjustment. The carbon cycle presents different but equally complex challenges. On Earth, this cycle involves carbon moving between the atmosphere as carbon dioxide, living organisms as organic compounds, oceans as dissolved carbon compounds, and geological reservoirs as carbonates and fossil fuels. In a terraforming context, establishing this cycle would mean creating not just the biological components, but also geological and chemical processes that can operate at planetary scales. For Mars, the initial carbon challenge involves liberating enough carbon dioxide to warm the planet and create sufficient atmospheric pressure. Much of Mars carbon is believed to be locked in subsurface carbonates and polar dry ice deposits. Once mobilized into the atmosphere, this carbon would need to be gradually incorporated into developing ecosystems through photosynthesis. This would require introducing increasingly complex plant communities capable of surviving Martian conditions, beginning with algae and lichens and eventually progressing to higher plants. However, plants alone cannot sustain a carbon cycle. Decomposers, bacteria, and fungi that break down dead organic matter and return carbon to the soil and atmosphere would be essential partners in the developing system. These decomposer communities would need to be specially designed for the unique soil chemistry of Mars, with its high iron content and presence of compounds like perchlorates that are rare on Earth. The hydrological cycle, the movement of water between atmosphere, surface, and subsurface, represents perhaps the most visible biogeochemical cycle and one of the most challenging to establish on Mars. Earth's water cycle depends on a complex interplay between temperature, pressure, and geography that drives evaporation, cloud formation, precipitation, and groundwater movement. Replicating this on Mars would require not just adding water through asteroid imports or subsurface ice melting, but creating the atmospheric conditions that allow water to remain liquid and cycle through the environment rather than being lost to space or frozen permanently. Initial water cycling would likely be restricted to enclosed environments or low-lying areas where higher atmospheric pressure could be maintained. Over centuries, as the atmosphere thickens, these water-active regions could expand, gradually developing the planet-wide precipitation patterns needed for large-scale ecosystems. The design of terrain features to capture and channel limited water resources would be crucial during early phases when liquid water remains scarce. The phosphorus cycle highlights the particular challenge of non-atmospheric cycles. Unlike carbon and nitrogen, phosphorus has no significant gaseous phase in its natural cycle. On Earth, it moves primarily through weathering of rocks, uptake by plants, transfer through food chains, and return to soil through decomposition or marine sediment deposition. For terraformed worlds, the limited availability of biologically accessible phosphorus could create serious ecosystem constraints. Engineers would need to identify and process phosphorus-rich areas of the Martian crust to make this essential nutrient available to developing ecosystems. Microorganisms specifically designed to solubilize phosphorus from Martian rocks would be key to this process. Without sufficient phosphorus cycling, even ecosystems with adequate carbon and nitrogen would face severe productivity limitations, as phosphorus is essential for DNA, ATP, the energy currency of cells, and cell membranes. The interconnected nature of these cycles creates both challenges and opportunities. Interventions in one cycle inevitably affect others, sometimes in non-intuitive ways. For instance, increasing nitrogen availability might boost plant growth, accelerating carbon uptake from the atmosphere, but also increasing demand for phosphorus and water. These complex interdependencies would require comprehensive monitoring systems tracking elemental flows throughout the developing planetary system. The time required to establish functioning biogeochemical cycles would likely exceed the engineering timeframes for physical terraforming infrastructure. While atmospheric composition might be modified within centuries, developing the biological communities that maintain stable elemental cycling could take millennia. Earth's current cycles develop through billions of years of coevolution between organisms and their environment. Telescoping this into even a few thousand years represents an unprecedented biological engineering challenge. The establishment of these interconnected cycles would likely follow a progression from simple, robust systems toward increasing complexity and stability. Initial cycles would focus on a few key organisms performing essential functions, with redundant systems and frequent human intervention to maintain balance. As the system matures, greater biodiversity would provide natural resilience, eventually reaching a state where human management shifts from constant adjustment to occasional steering of natural processes. Creating self-sustaining biogeochemical cycles represents perhaps the most profound aspect of terraforming, the point where engineering gives way to ecology and a constructed environment begins to maintain itself through the same natural processes that operate on Earth. Success would be measured not by the completion of specific infrastructure projects, but by the moment when introduced ecosystems begin functioning independently, cycling elements through the environment without continuous human intervention, truly making another planet alive. The immense technical challenges of terraforming, from resource acquisition to biogeochemical engineering, are matched by equally complex social challenges related to governance and legal structures. The transformation of entire planets would require decision-making frameworks, legal principles, and governance institutions unlike anything in human history, operating across timescales far beyond traditional political or legal horizons. Current space law provides an insufficient foundation for managing terraforming projects. The cornerstone document of international space law, the Outer Space Treaty of 1967, establishes important principles including the prohibition of national appropriation of celestial bodies and the requirement that space activities benefit all countries. However, it was drafted long before terraforming became a serious scientific consideration and contains no specific provisions for planetary modification. The treaty's declaration that celestial bodies are the province of all mankind raises fundamental questions about who could authorize planet-wide terraforming. Does transforming a planet constitute a form of appropriation prohibited by the treaty? Would benefits from terraformed planets need to be shared among all nations, even those that didn't contribute to the effort? These questions reveal the gaps in existing legal frameworks when confronted with the prospect of planetary-scale engineering. New legal instruments specifically addressing terraforming would be necessary before any large-scale project could begin. These would likely take the form of international treaties establishing principles, permissions, and limitations for planetary modification. Key provisions would include environmental assessment requirements, reversibility standards, and benefit-sharing arrangements to ensure that terraforming serves humanity's collective interests rather than just those of spacefaring powers. The question of ownership presents particularly thorny legal challenges. While the Outer Space Treaty prevents nations from claiming sovereignty over celestial bodies, it doesn't clearly address rights to use transformed environments. Would settlers on a terraformed Mars have property rights to the land they occupy? Could regions of a transformed planet be administered by particular nations or organizations that contributed to terraforming efforts? Resolving these questions would require new legal concepts that balance incentives for investment with principles of common heritage. The multi-generational nature of terraforming necessitates governance structures designed for extraordinary time horizons. Most human institutions struggle to maintain consistent policies across decades, let alone the centuries or millennia required for planetary transformation. Terraforming governance would need mechanisms to ensure commitment across multiple generations while remaining adaptable to new information and changing circumstances. One proposed approach involves the creation of specialized terraforming authorities with constitutions and decision-making structures specifically designed for extreme longevity. These institutions might incorporate elements like staggered, very long-term appointments for leadership, constitutional provisions that can only be changed with overwhelming consensus, and built-in roles for representatives of future generations. Some proposals suggest incorporating advanced artificial intelligence systems to maintain institutional memory and policy consistency across centuries. Conflict resolution mechanisms would be essential components of terraforming governance. Disputes would inevitably arise over resource allocation, technical approaches, timelines, and countless other aspects of these complex projects. Traditional international dispute resolution through courts or diplomatic channels operates too slowly for technical projects where delays could have cascading consequences. Specialized arbitration systems with both technical expertise and legal authority would be needed to resolve conflicts without derailing progress. The equitable distribution of both costs and benefits presents another governance challenge. Terraforming would require enormous investments over timeframes that exceed normal economic planning horizons. The costs would include not just financial resources, but also scientific talent, material resources, and opportunity costs from pursuing planetary transformation rather than other human priorities. Ensuring that these costs are shared fairly among participating entities would require new economic and political frameworks. frameworks. The benefits of terraforming, potentially including new habitable land, resource access, scientific knowledge, and technological development, would likewise need equitable distribution mechanisms. Historical precedents from Earth's colonization eras demonstrate the potential for exploitation when new territories become accessible, with indigenous populations and less powerful groups often excluded from benefits. Terraforming governance would need to proactively address these concerns through benefit-sharing requirements, access guarantees for developing nations, and protections for communities established during early settlement phases. Decision-making authority presents particularly complex governance questions. Who has the right to make fundamental choices about planetary transformation targets and methods? Democratic principles suggest broad participation in such momentous decisions, but practical realities might limit meaningful involvement to those with relevant expertise or resource contributions. Balancing technical efficiency with inclusive decision-making would require new governance models that might include tiered systems with different stakeholders having authority over different aspects of the terraforming process. The creation of regulatory frameworks for terraformed environments would represent another governance challenge. As transformed planets develop atmospheres, hydrospheres, and eventually biospheres, regulations would be needed to manage resource use, prevent pollution, protect developing ecosystems, and ensure safe human habitation. These regulatory systems would need to evolve alongside the changing planetary environments they govern, starting with basic safety rules for early settlements and eventually developing into comprehensive environmental protection regimes for mature terraformed worlds. Implementation of terraforming governance would likely occur in phases corresponding to project development stages. Initial frameworks might focus on research protocols and impact assessments, followed by resource management systems as material collection begins. As actual transformation proceeds, governance would expand to include environmental monitoring, settlement management, and ecosystem protection. The final phases would involve transitioning from project governance to permanent planetary administration as terraformed worlds become self-sustaining. The development of effective governance for terraforming wouldn't just benefit planetary transformation projects. The legal principles, institutional designs, and decision-making frameworks created for these multi-century endeavors could inform approaches to other long-term challenges facing humanity, from climate change to nuclear waste management to intergenerational resource stewardship. In this way, the governance innovations necessitated by terraforming might help humanity develop the long-term thinking capabilities needed to address its most persistent challenges both on and off Earth. While effective governance frameworks would guide terraforming projects at the institutional level, the immense technical challenges of transforming Venus would require specialized approaches that address its unique atmospheric conditions. Among these challenges, the sequestration of Venus's massive carbon dioxide atmosphere stands as perhaps the most formidable hurdle in making the planet habitable. Venus possesses an atmosphere approximately 90 times more massive than Earth's, composed primarily of carbon dioxide that creates surface pressures equivalent to being nearly 1 kilometer deep in Earth's oceans. This enormous carbon reservoir, estimated at more than 1 quadrillion tons, would need to be drastically reduced before any meaningful surface habitability could be achieved. The sheer scale of this task dwarfs even the most ambitious carbon capture proposals for Earth. Several approaches have been proposed for Venusian atmospheric carbon sequestration, each operating at scales barely conceivable by today's standards. One of the most direct methods would involve converting atmospheric carbon dioxide into stable mineral carbonates through reactions with silicate rocks. On Earth, this weathering process occurs naturally but very slowly. On Venus, it would need to be dramatically accelerated through engineered chemical processes. Floating chemical processing factories deployed in the more temperate upper atmosphere could capture carbon dioxide and combine it with pulverized silicate minerals, perhaps derived from Venus's surface or delivered from asteroid mining operations. The resulting carbonate compounds would be physically stable, effectively locking away carbon for geological timeframes. The challenge lies not in the chemistry, which is well understood, but in the industrial scale required, which would exceed Earth's entire current manufacturing capacity many times over. Biological approaches offer an alternative pathway. The upper atmosphere of Venus, at altitudes of approximately 50 kilometers, has temperatures and pressures remarkably similar to Earth's surface conditions. Engineered photosynthetic organisms, likely algae modified to survive the sulfuric acid clouds, could be introduced to these regions to convert convert carbon dioxide into oxygen and organic carbon compounds. As these organisms multiply and eventually die, their carbon-rich remains would rain down toward the surface, effectively transferring carbon from the atmosphere to the surface in stable forms. This biological sequestration would need to operate on an unprecedented scale. Scientists estimate that photosynthetic organisms covering thousands of square kilometers of Venus's upper atmosphere would be required to make meaningful progress over centuries. The organisms would need extensive genetic modifications, not just to survive the acidic environment, but also to perform photosynthesis efficiently under Venusian conditions and to reproduce reliably without additional Earth-supplied nutrients. Advanced nanotechnology represents a more speculative approach. Self-replicating nanomachines designed to capture carbon dioxide molecules and restructure them into useful solid forms could theoretically process the Venusian atmosphere if deployed in sufficient numbers. These machines might convert atmospheric carbon into structurally useful materials like carbon nanotubes or graphene sheets, which could later be used for construction purposes. While far beyond current capabilities, this approach aligns with the long-term technological development that would occur alongside multi-century terraforming efforts. Chemical catalysis using hydrogen provides another promising avenue. Introducing hydrogen to the Venusian atmosphere, perhaps harvested from the gas giants or water-rich asteroids, would allow reactions that convert carbon dioxide into solid carbon and water vapor through variations of the Bosch reaction. This approach offers the dual benefit of reducing carbon dioxide while simultaneously generating water, another resource essential for habitability. The energy requirements would be enormous, but the chemistry follows well-established principles. Orbital processing represents yet another possibility. Massive atmospheric scoops in Venus orbit could physically remove portions of the upper atmosphere for processing in space-based factories. The carbon could be sequestered in solid forms or potentially utilized for space-based manufacturing and construction. This approach would require space infrastructure far beyond current capabilities, but would allow precise control over atmospheric composition and pressure reduction. Regardless of the specific approach, carbon sequestration efforts would need to address several practical challenges. The energy requirements would be enormous. Estimates suggest that removing just 1% of Venus's atmosphere annually would require power equivalent to hundreds of times Earth's current global energy production. This energy would likely need to come from space-based solar arrays capturing the intense sunlight available closer to the Sun. The disposal or utilization of the sequestered carbon presents another challenge. If converted to solid forms, the volume of material would be enormous, equivalent to mountain ranges of carbonates or carbon-based materials. Some could be used for construction of habitats or infrastructure, but much would simply need to be stored in stable formations on the Venusian surface. This stored carbon would need to remain stable under changing planetary conditions as terraforming progresses. The time frame for meaningful carbon reduction, even with the most advanced proposed technologies, would span many centuries. Early efforts might reduce atmospheric pressure by perhaps 1% per century, with rates potentially accelerating as infrastructure expands and technologies improve. The process would continue until reaching an atmospheric pressure perhaps 2 to 5 times Earth's, still higher than our home planet, but potentially manageable with minimal adaptation for human inhabitants. The carbon sequestration technologies developed for Venus would likely have applications for Earth's own climate challenges. While Earth's excess atmospheric carbon is minuscule compared to Venus, the principles and techniques developed for Venusian transformation could inform more efficient approaches to terrestrial carbon capture. This represents one of many potential technological spin-offs from terraforming research that could benefit Earth directly. The massive scale of Venus's atmospheric transformation highlights why terraforming would necessarily be an incremental, phased process spanning many human generations. During these extended transformation periods, humans would need to establish presence on partially terraformed planets through specialized habitats that bridge the gap between current planetary conditions and the distant goal of Earth-like habitability. Transitional habitats would serve as both living spaces for terraforming workers and test beds for technologies and biological systems intended for eventual wider deployment. These structures would evolve alongside planetary conditions, gradually opening to increasingly Earth-like environments as transformation progresses. The design of effective transition transitional habitats represents a crucial engineering challenge that would enable human presence throughout the centuries-long terraforming process. For Mars, early transitional habitats would likely take the form of pressurized domes or underground facilities providing Earth-like internal conditions while shielded from the harsh Martian environment. These enclosed environments would need to maintain suitable atmospheric pressure, filter harmful radiation, regulate temperature, and provide all life support requirements for inhabitants. Early versions would rely heavily on materials imported from Earth, but as in situ resource utilization capabilities develop, locally sourced materials would increasingly dominate construction. The most promising locations for initial Martian habitats would be subsurface environments, potentially utilizing natural lava tubes or excavated caverns. These underground spaces offer several advantages: natural protection from radiation and micrometeorites, insulation from extreme temperature fluctuations, and potential access to subsurface ice deposits. Initial habitats might house dozens to hundreds of people in relatively cramped conditions, focused primarily on establishing the infrastructure needed for larger settlements. As terraforming progresses and surface conditions begin to improve, habitats would gradually transition to more surface-integrated designs. Transparent dome materials capable of filtering harmful radiation while allowing visible light would create spaces where Earth plants could grow directly in treated Martian soil. These biological test zones would serve dual purposes, providing psychological benefits for inhabitants through green spaces while testing organisms intended for eventual release into the broader environment. The challenge of maintaining these habitats would evolve over time. Early structures would require complete life support recycling and external energy sources. As planetary conditions improve, habitats could increasingly breathe the thickening Martian atmosphere, perhaps initially just extracting carbon dioxide for plant growth, but eventually using the atmosphere more directly as oxygen levels increase. This gradual opening to the environment would reduce resource requirements while providing valuable data on the progress of planetary transformation. For Venus, transitional habitats would take a dramatically different form. The crushing pressure and extreme heat of the Venusian surface makes ground-based habitats impossible during early terraforming phases. Instead, floating habitats suspended in the upper atmosphere, approximately 50 to 60 kilometers above the surface, would provide viable living conditions. At these altitudes, temperature and pressure are remarkably Earth-like, requiring far less structural engineering than surface facilities on Mars. These cloud cities would essentially be massive dirigibles filled with breathable air, which would naturally float in Venus's dense carbon dioxide atmosphere. The habitats would need protection from sulfuric acid clouds, but could otherwise provide relatively comfortable living conditions. Their mobility would allow them to avoid severe storms and position themselves optimally for both human comfort and oversight of terraforming operations below. As Venus's atmosphere gradually thins and surface temperatures decrease, transitional habitats would begin to establish connections with the surface. Initially, these might be automated processing facilities remotely controlled from the cloud habitats. Later, mountaintop outposts could be established as the highest elevations become cool enough for heavily protected structures. Only after centuries of atmospheric transformation would permanent surface habitats become viable, likely first in the form of pressurized domes similar to early Martian designs. The construction materials for transitional habitats would evolve alongside terraforming progress. Early structures would rely heavily on imported materials and those that could be harvested from the upper atmosphere or asteroids. As transformation advances, increasingly local resources would be incorporated: processed regolith for Martian habitats or materials extracted from the cooling Venusian surface. This transition from imported to local resources represents a critical path towards self-sufficiency for terraforming colonies. Life support systems within these habitats would serve as microcosms of the larger terraforming effort. Closed-loop ecological systems recycling air, water, and nutrients would provide essential life support while demonstrating principles intended for planetary-scale implementation. These controlled environments would allow testing of engineered organisms and ecological relationships before releasing them into the broader planetary environment. The social dynamics within transitional habitats would shape developing planetary cultures. Living for generations in these partially enclosed environments would foster unique cultural adaptations and specialized knowledge. Habitat communities would likely develop distinct identities and approaches to the terraforming process, potentially leading to different visions for the planet's ultimate development. Managing these emerging cultural differences would become an important aspect of terraforming governance. The gradual transition from fully enclosed habitats to increasingly open interaction with transforming planetary environments would serve as both practical necessity and powerful psychological milestone. Each generation would experience a slightly more habitable planet than their predecessors, providing tangible evidence of progress in the multi-century terraforming effort. This visible improvement would help maintain the social commitment necessary for such long-term endeavors. The design principles developed for these transitional habitats would have applications beyond terraforming. The same technologies could enable human settlement throughout the solar system, from the moons of Jupiter to the asteroid belt, creating the infrastructure for a truly spacefaring civilization, regardless of whether full planetary terraforming is ultimately achieved. While transitional habitats would enable human presence during terraforming efforts on Mars and Venus, many scientists and engineers have suggested that the major planets might not be the most efficient targets for humanity's first terraforming endeavours. The moons of our solar system, particularly those orbiting the gas giants Jupiter and Saturn, offer intriguing alternatives that could potentially provide faster results with more manageable resource requirements. The comparison between terraforming moons versus planet centres on several key factors that significantly impact feasibility. Size represents the most obvious difference. Moons are substantially smaller than planets, meaning there's simply less volume of atmosphere to create or modify, and less surface area to transform. Titan, Saturn's largest moon and one of the most promising terraforming candidates, has a surface area approximately similar to all of Earth's continents combined, but only about 14% of Earth's total surface area. This smaller scale translates directly to reduced resource requirements and potentially shorter timeframes for meaningful transformation. Titan specifically offers several distinct advantages as a terraforming candidate. It already possesses a thick nitrogen atmosphere, similar in composition to Earth's but lacking oxygen. The atmospheric pressure at Titan's surface is approximately 1.5 times that of Earth, slightly higher than our home planet, but well within human tolerance with minimal adaptation. This existing atmosphere eliminates one of the most challenging aspects of Martian terraforming, the need to create sufficient atmospheric pressure from minimal existing resources. Additionally, Titan has abundant organic compounds in the form of liquid methane and ethane that form lakes and seas on its surface, along with complex hydrocarbons in its atmosphere. These organic materials could potentially be converted into more biologically useful compounds through engineered chemical or biological processes. The Moon also appears to have a subsurface water ocean, providing another essential resource for potential habitation if it could be accessed. Europa, one of Jupiter's largest moons, presents a completely different terraforming approach centered around its subsurface ocean. Scientists believe Europa contains more liquid water than all of Earth's oceans combined, hidden beneath an ice shell approximately 15 to 25 kilometers thick. Rather than terraforming the surface, which experiences intense radiation from Jupiter, efforts might focus on creating habitable spaces within this subsurface ocean, or in the boundary region between ice and ocean. The gravitational conditions on moons present both challenges and opportunities for terraforming. Most large moons have surface gravity significantly lower than Earth's. Titan's gravity is approximately 14% of Earth's, while Europa's is 13%. This reduced gravity would simplify construction of large structures and reduce energy requirements for transportation, potentially accelerating infrastructure development. However, long-term human habitation in low-gravity environments presents physiological challenges, including bone density loss and muscle atrophy. Any permanent settlements would need to address these health concerns, perhaps through rotating habitats that create artificial gravity or medical interventions that mitigate low-gravity effects. Radiation environments differ dramatically between various terraforming targets. Mars receives higher radiation levels than Earth due to its thin atmosphere and lack of magnetic field, but the radiation environment at many moons presents even greater challenges. Europa, for instance, receives extremely high radiation doses from Jupiter's intense magnetic field, which traps and accelerates charged particles from the solar wind. Surface habitation on Europa would be virtually impossible without extraordinary shielding, directing terraforming efforts toward its protected subsurface ocean. Titan, by contrast, benefits from Saturn's magnetosphere and its own thick atmosphere, which together provide substantial radiation protection comparable to or better than Earth's. This natural shielding eliminates one of the major challenges that Mars terraformers would face, making Titan potentially more immediately habitable from a radiation perspective. Temperature management presents different challenges for moons versus planets. Titan maintains a chilly surface temperature of approximately -179 degrees Celsius, far too cold for liquid water or Earth-like biology. Warming Titan would require massive heat generation, potentially through redirecting additional sunlight with orbital mirrors or through greenhouse gas production. However, once warmed, Titan's thick atmosphere would help retain heat effectively, potentially creating a more stable thermal environment than would be possible during early Martian terraforming. The distance from Earth creates logistical challenges for moon terraforming. The gas giant moons orbit much farther from Earth than Mars, increasing travel times and complicating supply chains. Communication delays would reach hours rather than minutes, requiring more autonomous operation of terraforming systems. However, these distances might be offset by the rich resource environments of the outer solar system, particularly the abundant volatiles that would be crucial for atmospheric development. Timeframes for meaningful terraforming might actually be shorter for certain moons despite their greater distance. The smaller scale, combined with advantageous starting conditions like Titan's existing atmosphere, could potentially allow more rapid progress toward habitability in contained regions. While planetary-scale terraforming might require millennia, creating habitable zones on portions of a moon might be achievable within centuries using similar technologies. Energy requirements for moon terraforming would differ substantially from planetary approaches. The outer solar system receives significantly less solar energy, making solar power less efficient. Terraforming efforts would likely rely more heavily on nuclear power, potentially including fusion reactors if that technology matures. Alternatively, massive solar collection systems many times larger than those needed for inner system terraforming could compensate for the reduced solar flux. The unique chemical environments of various moons would require tailored approaches. Titan's hydrocarbon-rich chemistry would necessitate different biological and chemical engineering than the iron-rich, oxidized environment of Mars. The potential availability of subsurface water on many outer solar system moons could provide crucial resources, but accessing these reservoirs through thick ice crusts presents significant engineering challenges. From a governance perspective, moon terraforming might face fewer legal complications than planetary transformation. The Outer Space Treaty's provisions regarding celestial bodies are generally interpreted to focus primarily on planets rather than moons, potentially creating more flexibility in how these bodies could be modified. Additionally, the more contained scale of moon terraforming might allow projects to proceed with less concern about unintended consequences spreading throughout an entire planetary system. The comparison between moon and planetary terraforming isn't a simple either-or proposition. Most likely, early terraforming efforts would target multiple bodies simultaneously, with lessons from each project informing approaches to others. The development of technologies for Mars or Venus terraforming would have direct applications to moon transformation and vice versa. Humanity's expansion throughout the solar system would likely follow a diverse approach, creating habitable niches across many types of environments rather than focusing exclusively on Earth-like planetary conditions. Whether terraforming targets planets or moons, one challenge remains consistent across all extraterrestrial environments: managing radiation exposure for both human inhabitants and introduced organisms. The radiation levels on Mars, Venus, and various moons significantly exceed Earth's surface conditions, creating a fundamental obstacle to long-term habitability that would need to be addressed throughout the terraforming process. Radiation in space environments comes from multiple sources, each presenting different management challenges. Galactic cosmic rays, high-energy particles originating from outside our solar system, can penetrate deep into materials and cause significant biological damage. Solar radiation includes both electromagnetic energy and charged particles, with solar flares and coronal mass ejections periodically releasing intense bursts of harmful radiation. Additionally, some bodies like Jupiter produce their own radiation belts that pose extreme hazards to nearby moons and any potential inhabitants. On Earth, we're protected from this harmful radiation by two main systems: our planet's magnetic field, which deflects charged particles, and our thick atmosphere, which absorbs much of the remaining radiation radiation before it reaches the surface. Any comprehensive radiation management strategy for terraformed environments would need to replicate these protections or provide alternative solutions. During early terraforming phases, when planetary atmospheres remain thin and magnetic protection might still be under development, human habitats would require significant physical shielding. The most effective materials for radiation shielding provide high electron density to block incoming particles. Water, concrete, and certain metals serve this purpose well. Early habitats would likely incorporate water reservoirs into their structural designs, providing both radiation protection and essential resource storage. Regolith, the loose surface material found on Mars, the Moon, and other bodies, offers another readily available shielding option. Habitats could be covered with several meters of packed regolith, providing protection comparable to Earth's atmosphere. Underground habitats would gain this protection naturally, explaining why subsurface construction would dominate early settlement phases on high radiation bodies like Mars. As terraforming progresses and atmospheres thicken, natural radiation protection would gradually improve. Scientists estimate that an atmosphere providing pressure similar to Earth's high mountains, about 50% of sea level pressure, would reduce radiation to levels where short-term exposure poses minimal risk, though still above Earth normal conditions. This creates the possibility for transitional periods where humans might venture outside habitats with minimal protection for limited durations before returning to more heavily shielded living quarters. Biological radiation protection would develop alongside physical shielding. Plants genetically engineered for terraforming environments could include high concentrations of radiation-absorbing compounds in their tissues. Forests of such plants might serve dual purposes, contributing to oxygen production while creating radiation shadows where exposure levels are reduced. Some scientists have proposed creating upper atmospheric layers rich in hydrogen-containing compounds that would be particularly effective at absorbing cosmic radiation. For human inhabitants of partially terraformed environments, medical approaches would complement environmental protections. Pharmaceutical radiation protectants could help cells repair DNA damage from radiation exposure. Gene therapy might enhance natural DNA repair mechanisms or introduce new protective systems based on extremophile organisms from Earth that demonstrate extraordinary radiation resistance, like the bacterium Deinococcus radiodurans, which can survive radiation doses thousands of times greater than would kill a human. Personal protective equipment would evolve alongside terraforming progress. Early settlers might require full pressure suits with integrated radiation shielding for any surface activities. As conditions improve, this could transition to lighter weight clothing, incorporating radiation-absorbing materials, perhaps similar to the lead aprons used during medical X-rays, but made from more advanced materials optimized for the specific radiation spectra encountered. Constant monitoring of radiation conditions would be essential throughout terraforming projects. Networks of radiation detectors would track background levels and provide early warnings of solar events that temporarily increase exposure risks. This monitoring infrastructure would allow habitat systems to adjust shielding configurations and alert residents to seek additional protection during high radiation periods. The radiation challenges would vary significantly between terraforming targets. Mars receives approximately twice the radiation of Earth's surface due to its thin atmosphere and lack of magnetic field. Venus, despite lacking a strong intrinsic magnetic field, receives less radiation at its surface because its extremely thick atmosphere provides substantial shielding, though accessing this protection requires first addressing the extreme temperature and pressure conditions. The moons of Jupiter face perhaps the most severe radiation environments, with Europa receiving radiation doses that would be lethal to unprotected humans in just days. The development of artificial magnetic fields, as previously discussed for Mars, would provide crucial radiation protection that atmosphere alone cannot offer. While thick atmospheres can block many forms of radiation, charged particles can become trapped in planets' magnetic fields, creating zones of concentrated radiation similar to Earth's Van Allen belts. Carefully designed magnetic field generators would need to consider these effects to avoid inadvertently creating high radiation regions that could threaten surface settlements. Plants and microorganisms introduced during terraforming would require their own radiation adaptations. Early terraforming species would need substantial genetic modifications to survive the higher radiation environments of partially transformed planets. These might include enhanced DNA repair mechanisms, redundant copies of critical genes, and improved antioxidant systems to manage the cellular damage caused by radiation exposure. As terraforming progresses and radiation levels decrease, less heavily modified organisms could be introduced, gradually transitioning toward more Earth-like species. The radiation management strategies developed for terraforming environments would have valuable applications for space exploration more generally. Better radiation shielding, biological protection systems, and medical countermeasures would benefit everything from crewed missions to Mars to long-duration space habitation. The necessity of addressing radiation challenges for terraforming would likely accelerate development of these technologies, potentially opening the broader solar system to human exploration even before terraforming goals are achieved. The development of radiation management strategies for extraterrestrial environments draws heavily upon our experiences modifying and engineering Earth's own systems. This relationship between terrestrial geoengineering and planetary terraforming represents more than just casual similarity. Many of the technologies being developed to address climate change and environmental challenges on Earth would serve as direct precursors to the tools needed for transforming other planets. Earth's ongoing climate crisis has accelerated research into various climate intervention techniques that have direct applications to terraforming. Solar radiation management approaches being studied to cool Earth, including stratospheric aerosol injection and cloud brightening, could be reversed and adapted for warming Mars. Scientists developing these technologies have created sophisticated computer models predicting how atmospheric particles affect planetary energy balance. The same models, recalibrated for Martian conditions, could help engineers determine exactly what types and quantities of materials would most efficiently trap heat in the thin Martian atmosphere. Carbon dioxide removal technologies represent another area where Earth-based development directly supports terraforming capabilities, methods being refined to pull carbon from Earth's atmosphere, including direct air capture systems and enhanced weathering techniques, are essentially the same technologies that would be needed in vastly larger scales to process Venus's atmosphere. The current challenge of removing billions of tons of carbon from Earth's atmosphere is a useful stepping stone toward the much larger challenge of processing Venus's quadrillion plus tons of atmospheric carbon dioxide. Water management technologies developed for Earth's arid regions would be crucial for early Martian settlement and terraforming. Advanced desalination systems designed for water-stressed regions could be adapted to extract pure water from the briny subsurface liquid that appears to exist on Mars. These systems are becoming increasingly energy efficient on Earth, a critical factor for resource-constrained early Martian settlements. Similarly, atmospheric water harvesting technologies that collect moisture from desert air would be directly applicable to extracting the minimal water vapor present in Mars's atmosphere during warmer periods. Soil remediation techniques developed to restore contaminated industrial sites on Earth provide valuable insights for making Martian regolith suitable for Earth life. The perchlorate compounds that make Martian soil toxic to most Earth organisms are chemically similar to contaminants found at certain Earth industrial sites. Bioremediation approaches using specialized bacteria to break down these compounds are already being adapted in laboratories specifically for Martian soil composition. These biological cleaning systems would likely precede any large-scale introduction of plants to the Martian surface. Arid land reclamation projects across Earth's deserts demonstrate techniques directly relevant to creating viable soil from Martian regolith. The addition of organic matter, specific mineral supplements, and microbial communities to stabilize desert soils mirrors the process that would be needed to transform fine Martian dust into productive growing medium. Large-scale desert greening projects in China and the Middle East serve as partial analogues for the initial stages of Martian surface transformation, though operating under the much more favorable conditions of Earth's atmosphere and gravity. Earth's extreme environment research facilities provide testing grounds for terraforming technologies. Antarctica research stations function essentially as miniature versions of what early Martian bases would require. Closed systems operating in a hostile environment with minimal external resources. The lessons learned about sustainability, resource recycling, and psychological adaptation in these isolated outposts directly inform plans for early terraforming settlements. Similarly, closed ecological systems like Biosphere 2, despite its well-documented challenges, provided valuable data about the complexity of creating self-sustaining environments, highlighting the difficulties that would be magnified at planetary scales. Ocean fertilization experiments conducted to study carbon sequestration exploration in Earth's oceans provide insights into how similar approaches might jumpstart simple ecosystems in newly created Martian seas. These experiments have revealed the complex and sometimes unpredictable responses of biological systems to human intervention, lessons that would be crucial when attempting to establish new aquatic ecosystems on a terraformed world. Weather modification technologies, though still limited in their Earth applications, would be essential for managing the developing climate systems of a terraforming planet. Cloud seeding techniques, currently used to enhance rainfall in some regions, would need to be dramatically scaled up and refined to help establish predictable precipitation patterns as water cycles develop on Mars. The atmospheric monitoring networks and predictive models developed for Earth weather modification would provide the foundation for the more comprehensive planetary weather management required during terraforming. Perhaps most importantly, the governance frameworks being developed for Earth's geoengineering provide precedents for managing large-scale planetary modification. The ethical debates, risk assessment protocols, and international cooperation mechanisms being established for potential climate intervention on Earth would inform the much larger governance challenges of terraforming. Earth's geoengineering governance serves as a testing ground for balancing scientific, political, and ethical considerations in planetary-scale environmental modification. The continued development of these Earth-based technologies serves dual purposes, addressing pressing environmental challenges on our home planet, while simultaneously advancing capabilities needed for potential terraforming. This synergistic relationship highlights how investment in Earth's environmental technologies might ultimately support humanity's expansion throughout the solar system, creating a practical pathway from current capabilities toward the much more advanced technologies terraforming would require. The practical knowledge gained from Earth's geoengineering efforts would be invaluable, but equally important are the economic systems that would make terraforming financially viable. The economics of terraforming represents perhaps the most radical departure from traditional financial thinking, requiring frameworks that operate across centuries and manage resources on a truly planetary scale. The sheer magnitude of investment required for meaningful terraforming exceeds anything in human economic history. Conservative estimates suggest that even initial Mars terraforming efforts would require funding equivalent to trillions of dollars in current terms, potentially exceeding the annual gross domestic product of the entire Earth. This extraordinary scale raises fundamental questions about how such projects could be financed and what economic structures could support multi-generational investment. Traditional economic models struggle with terraforming timeframes. Standard financial calculations heavily discount future returns through net present value formulas, effectively assigning minimal value to benefits realized centuries in the future. This approach makes little sense for projects like terraforming, where the most significant returns might come hundreds of years after initial investments. New economic frameworks would be needed that appropriately value long-term returns and incorporate broader metrics of success beyond direct financial profit. Several financing approaches have been proposed to address these challenges. Public funding through international consortiums could treat terraforming as a multi-generational public infrastructure project, similar to how nations fund basic scientific research or space exploration, but at vastly larger scales and timeframes. This approach would distribute costs across Earth's population while treating the transformed planets as common heritage of humanity. Alternatively, private investment models might leverage long-term property rights or resource claims as incentives. Companies or consortiums making early investments in terraforming infrastructure might secure development rights to certain regions or resources, creating financial instruments that could be traded long before the terraforming process completes. These rights would gradually increase in value as terraforming progresses, potentially providing returns even to early investors despite the multi-century development timeline. Hybrid public-private approaches seem most realistic, combining government funding for fundamental infrastructure with private investment in specific applications and settlements. This would mirror successful models from Earth's space industry, where government agencies develop core technologies and infrastructure while private entities build commercial applications on that foundation. The establishment of new financial instruments specifically designed for ultra-long-term projects would be crucial. Multi-generational bonds might pay small dividends for centuries before delivering major returns as terraforming milestones are achieved. Innovative insurance and risk-sharing mechanisms would help manage the inevitable setbacks and failures that would occur during such complex, long-duration projects. the economic value created by terraforming would be unprecedented. A successfully terraformed Mars would effectively double the habitable real estate available to humanity, creating an entirely new frontier for economic development. The value of this new territory, including land, resources, and development opportunities, would eventually dwarf the initial investment costs, but only after centuries of development. This delayed but enormous return creates unique challenges for economic planning. Terraforming would necessarily create entirely new industries and job categories that don't currently exist. Atmospheric engineers, planetary hydrologists, and ecosystem designers would become major professions. The supporting industries, from specialized equipment manufacturing to biological engineering, would employ millions. The educational and research institutions needed to train these specialists would themselves represent significant economic sectors. The resource flows needed for terraforming would reshape solar system economics. Asteroid mining operations supplying terraforming materials would eventually dwarf Earth's current mining industry. Transportation networks for moving people and materials between planets would require investment comparable to Earth's entire current transportation infrastructure. Energy production to power terraforming processes would necessitate capacity far exceeding current global energy systems. The economic governance of such massive long-term projects would require new institutions. Traditional corporations with their focus on quarterly earnings could not effectively manage centuries-long projects. New organizational forms, perhaps similar to sovereign wealth funds but with even longer timeframes, would need to emerge. These institutions would require carefully designed governance structures to maintain consistent direction across many human generations while remaining accountable to their stakeholders. The distribution of economic benefits would raise significant questions of equity and justice. Would the tremendous value created by terraforming flow primarily to the entities funding the process, or would broader distribution mechanisms ensure that humanity collectively benefits from these new worlds? The economic models developed to address these questions would need to balance incentives for investment with principles of common heritage and equitable access. The potential for resource conflicts would require robust economic regulations. As valuable resources are discovered on terraforming planets, competing claims could threaten project continuity. Preemptive establishment of resource rights frameworks, perhaps modelled on Earth's deep seabed mining regulations or Antarctic research protocols but adapted for planetary scales, would be necessary to prevent destabilizing conflicts. Labour economics in terraforming contexts would differ fundamentally from Earth norms. Early terraforming settlements would require highly specialized workers willing to accept difficult living conditions for the chance to participate in a historic endeavor. Later stages might involve larger populations engaged in more diverse economic activities as settlements mature. The transition between these phases would require careful economic planning to maintain workforce stability. Perhaps most profoundly, terraforming economics might require partial departure from pure market-based systems. The longest-term aspects of planetary transformation, those with payback periods exceeding multiple human lifespans, simply cannot generate the near-term returns that market systems demand. Some form of economic planning with very long time horizons would be necessary, potentially creating hybrid economic systems that combine market elements for shorter-term activities with more centralized planning for the longest-term terraforming functions. The economics of terraforming ultimately highlights the limitations of our current economic thinking when confronted with truly long-term civilization-scale projects. Successfully financing and managing such endeavors would require not just technological innovation, but economic innovation of equal magnitude. New ways of conceptualizing value, managing resources, and making investment decisions that extend beyond typical human planning horizons. While developing economic frameworks for planetary transformation, scientists and engineers have also been conducting practical experiments that could be considered micro-terraforming, small-scale manipulations of Earth's most extreme environments to test techniques that might eventually apply to other worlds. These terrestrial test cases provide valuable data about the challenges of creating habitable conditions in hostile settings, while operating at scales more manageable than entire planets. The most well-known micro-terraforming experiment, Biosphere 2, offers particularly relevant lessons for planetary transformation. Constructed in the Arizona desert in the early 1990s, this 3-acre enclosed ecosystem attempted to create a self-sustaining environment with representative biomes including rainforest, desert, savanna, and even a miniature ocean. 8 people lived inside for 2 years, growing their own food and depending on the facility's internal ecosystems to recycle air, water, and nutrients. While the project encountered significant challenges, including unexpected oxygen depletion and management controversies, it provided invaluable data about the complexities of creating artificial ecosystems. The oxygen problems in Biosphere 2 proved especially instructive for terraforming scientists. Oxygen levels within the facility declined unexpectedly, eventually falling from the normal 21% to about 14%. Equivalent to conditions at elevations of 14,000 feet. Investigators later determined that microbes in the enriched soil were consuming oxygen faster than plants could produce it, and concrete in the structure was absorbing oxygen through carbonation reactions. This unforeseen interaction between biological and chemical systems mirrors the types of complex, emergent challenges that would arise during planetary terraforming, but at a scale where adjustments and learning remained possible. Antarctic research stations represent another form of micro-terraforming, demonstrating how humans can create habitable environments in one of Earth's most Mars-like settings. The dry valleys of Antarctica have been described by scientists as the most Mars-like environment on Earth, with extremely low temperatures, minimal precipitation, and limited biological activity. Research outposts in these regions must provide complete life support for inhabitants while minimizing environmental impacts, exactly the challenge faced by early Martian settlements. The engineering solutions developed for Antarctic stations, including efficient water recycling, waste management, and energy systems that function in extreme cold, provide proven technologies that could be adapted for early terraforming habitats. Desert reclamation projects across Earth offer insights into transforming barren landscapes into biologically productive environments. The Chinese government's efforts to halt the spread of the Gobi Desert through massive tree planting initiatives demonstrate techniques for stabilizing soil, altering local microclimates, and establishing pioneer species in hostile conditions. While Earth deserts benefit from atmospheric pressure and composition suitable for life, advantages not present on Mars or Venus, the methodologies for establishing vegetation in nutrient-poor soils with minimal water have direct applications to early terraforming efforts. Experiments in revitalizing contaminated industrial sites provide particularly relevant experience for dealing with the toxic compounds present in Martian soil. The perchlorate compounds that make Martian regolith potentially harmful to Earth life are chemically similar to contaminants found at certain Earth industrial sites. Bioremediation approaches using specialized bacteria to break down these toxic compounds are being actively researched with Mars applications specifically in mind. These biological cleaning systems would likely precede any large-scale introduction of plants in Martian terraforming scenarios. Hypersaline environments like the Dead Sea and California's Mono Lake harbor extremophile organisms that thrive in conditions lethal to most Earth life. Scientists studying these organisms have identified genetic adaptations that allow survival in environments with chemical compositions similar to certain Martian surface features. Some researchers have begun experimental work introducing these organisms to simulated Martian soil compositions within laboratory containment, testing whether their adaptive capabilities could make them suitable as pioneer species in early terraforming efforts. High-altitude habitation provides another relevant analogue for low-pressure environments. Human settlements in the Andes and Himalayas at elevations above 15,000 feet demonstrate physiological adaptations to low oxygen conditions similar to what might be experienced in the early stages of atmospheric development on Mars. The design of habitats in these regions, including methods for maintaining comfortable temperatures with minimal energy input and architectural approaches that maximize efficient use of imported materials, offers practical examples for early Martian settlement design. Deep subsurface environments on Earth, including mines and cave systems, present opportunities to study isolated ecosystems that develop with minimal connection to surface conditions. These environments sometimes harbor unique microbial communities that have evolved independently for thousands or millions of years, potential analogues for how introduced organisms might adapt to subsurface habitats on Mars. Mining operations that create habitable spaces deep underground also provide practical experience in constructing and maintaining safe environments in naturally hostile settings. Artificial closed ecological systems of increasing sophistication continue to be developed, building on lessons from both Biosphere 2 and Space Agency research into life support systems. The European Space Agency's Melissa project, Microecological Life Support System Alternative, aims to create a closed-loop system using microorganisms and plants to recycle air, water and waste while producing food. Essentially, a highly engineered miniature version of the processes needed for planetary life support. This research directly addresses the challenges of creating self-sustaining biological systems that could eventually support terraforming. Volcanic regions offer yet another important analog environment, particularly for understanding how life might be established on worlds with active geological processes. The colonization of fresh lava flows by pioneer organisms demonstrates natural succession processes that could inform terraforming strategies. These environments also provide opportunities to study how life adapts to high levels of potentially toxic elements, similar to those found in Martian regolith. While these Earth-based experiments provide crucial data, they all benefit from background conditions, including Earth's gravity, magnetic field, and atmospheric pressure that differ significantly from other planets. The next logical step in micro-terraforming research would be conducting larger-scale experiments in space environments, perhaps in specialized facilities on the Moon or in large rotating habitats that could simulate different gravitational conditions. These more advanced test environments would allow scientists to address additional variables that cannot be adequately simulated in Earth-based systems. The experience gained from these terrestrial micro-terraforming projects highlights a fundamental question that shapes all discussions of human expansion beyond Earth. Should we focus our efforts on modifying planetary environments to suit human needs? Or should we instead adapt ourselves to survive in the environments we encounter? This tension between terraforming and human adaptation represents one of the most significant strategic choices facing our species as we consider our future beyond Earth. The traditional vision of terraforming assumes that transforming planets to approximate Earth conditions represents the optimal path for human expansion into space. This approach maintains human biology essentially unchanged while engineering entire worlds to support it, a planet-centric solution that maximizes compatibility with our existing physiological requirements and technological systems. The appeal is obvious. Humans could eventually walk on Martian or Venusian surfaces with minimal protective equipment, breathing the atmosphere and living largely as they do on Earth. However, this approach faces enormous technical challenges, resource requirements, and time frames as we've explored throughout our discussion. Even with advanced technology, transforming an entire planet requires centuries or millennia of sustained effort. The question naturally arises, might it be more efficient to adapt humans instead? Human adaptation could take multiple forms, ranging from technological augmentation to genetic engineering. Specialized equipment already allows astronauts to survive in the vacuum of space for limited periods. More advanced pressure suits with closed-loop life support systems could potentially enable extended activity on the Martian surface, even without atmospheric transformation. Mechanical enhancements like exoskeletons could compensate for different gravitational environments, allowing humans to function efficiently on low-gravity worlds without the physiological deterioration normally associated with such conditions. More profound adaptations would involve direct modification of human biology through genetic engineering or cybernetic integration. Genetic modifications might enhance radiation resistance by improving cellular repair mechanisms or introduce greater tolerance for atmospheric compositions different from Earth's. Scientists have already identified genetic variants in high-altitude human populations that improve oxygen utilization. Similar adaptations could potentially be engineered for low-pressure environments like Mars. More speculative possibilities include adaptations for different gravity regimes or temperature ranges, potentially allowing humans to thrive in conditions that would be harmful to unmodified individuals. The cybernetic approach would integrate technological systems directly with human biology, creating partially mechanical organisms better suited to non-Earth environments. Neural interfaces might allow direct connection to environmental sensors and protective systems, effectively extending human sensory capabilities while providing instantaneous warning of environmental hazards. Internal medical systems could continuously monitor and adjust body chemistry to compensate for environmental stresses or provide supplemental oxygen in low-pressure conditions. A middle path between full planetary transformation and complete human adaptation involves targeted environmental modification, creating localized habitable zones rather than transforming entire planets. This para-terraforming approach might involve networks of connected habitats with Earth-like internal conditions while leaving most of the planet in its natural state. Advanced materials could allow construction of domed cities spanning tens of square kilometers, large enough to develop self-sustaining internal ecosystems, while requiring far fewer resources than planetary-scale transformation. The relative efficiency of these approaches depends partly on scale. For small populations, human adaptation or localized habitats likely requires fewer total resources than planetary terraforming. However, as population sizes increase, the efficiency calculation shifts. Maintaining thousands or millions of individually adapted humans or pressurized habitats eventually requires more total energy and resources than transforming the shared environment once, creating a crossover point where terraforming becomes the more efficient long-term strategy. The question also involves timescale considerations. Human adaptation through technology can be implemented within years or decades, essentially immediate compared to the centuries required for meaningful planetary transformation. This temporal advantage might make adaptation the preferred approach for initial expansion, with terraforming as a longer-term project that proceeds in parallel with established human presence. Ethical considerations further complicate this comparison. Genetic modification of humans raises significant concerns about consent, identity, and potential creation of specialized human subspecies adapted to different environments. If adaptation were pursued through genetic engineering, would children born into space settlements have a right to physiology that allows them to return to Earth? Would distinct human subspecies optimized for different planetary environments eventually develop divergent cultures and interests? From a practical standpoint, most expansion scenarios would likely involve a combination of approaches rather than an either-or choice. Early settlements would rely heavily on technological adaptation and enclosed habitats while initiating the longer-term processes of environmental transformation. As terraforming progresses, the degree of required human adaptation would gradually decrease. Different environments might justify different balances. Mars might merit full terraforming due to its relative similarity to Earth, while adaptation might remain the preferred approach for more exotic environments like Europa's subsurface ocean or Titan's hydrocarbon lakes. This hybrid strategy acknowledges both the immediate practicality of human adaptation and the long-term benefits of creating Earth-like environments. It recognizes that our species' greatest strengths include both our ability to engineer our surroundings and our capacity to adapt ourselves through technology and potentially biology. By pursuing multiple approaches simultaneously, humanity could establish presence throughout the solar system while maintaining the flexibility to adjust strategies as technologies mature and initial settlements provide practical experience with the challenges of extraterrestrial habitation. The tension between transforming planets and transforming ourselves ultimately reflects deeper questions about human identity and our relationship with the environments we inhabit. As we develop the capabilities that would make either approach possible, we will need to carefully consider not just what we can do, but what kind of spacefaring civilization we wish to become.